The playing musical chairs back there. I mean, that's fine. Okay. Just trying to balance out the numbers. It does work out 3, 3, 3, 4, 2. Okay. This is the odd one out, but and that's fine. Okay. That's it's always somebody else's fault. Yeah. Okay. So as you're completing that, what we would like to have you do if I can find the page number myself. I guess we'll start on page 77. Kind of take a gander at some of that information. Page 77, please. Okay, so we'll try to get that done.
Oh, they highlighted all the good stuff.
Okay, so probably the most important information as you see on page 77 is going to be any element's atomic number, because we know that if you are referring to element 28, you could just look at the table and it tells you you're discussing which element. Okay? And it's also that atomic number that gives you a specific number of what in that atom's nucleus. What's true about the atomic number? Gives you something very specific. Yeah, number of protons. That's right. That's how it identifies the element that you're referring to. Okay. So somewhat of a little bit of review from what you had learned 2 years ago, and we'll find out, well, how much are we going to retain from 2 years ago? Hopefully quite a bit. With that, we'll cover just a little more information, a little more quicker than what you would have done 2 years ago in the chemistry portion of physical science. For instance, that of the electrons, you did Bohr models with that. That meant you had those circles that you had the electrons going around in a circle. We referred to that. Also, if you remember, configuration was just a linear depiction of that, where you wrote 1s2, 2s2, 2p6. Could you utilize that slide rule as well? We'll be utilizing that in the near future. That's not until chapter 4. But what we want to be referring to is looking at that constant that you wrote up on the board yesterday, which was 6.022 times 10 to the 23rd. I think we just named what that was once. We only said it once, I think. It was called Avogadro's number. Okay, so we'll be utilizing that constant today. So what I want you to do is turn to page 83 now. Okay. So when we look at page 83, we see what's on the top called the mole, right? And it's sometimes hard to visualize what that means when we're referring to something called the mole, but on top of page 83, it says the mole is SI unit amount amount of a substance. A mole is the amount of substance that contains as many particles as there are in atoms and exactly 12 grams of carbon. The mole is a counting unit, just like a dozen is, okay? So what they're saying is if you're getting 3 dozen eggs, we all know that that's how many? 36. Just like when we looked at this tabletop, rather than referring to the length of this as 96 inches every time, you can just make it simpler by using what smaller number? 8. So 8 feet rather than 96 inches. So this, again, this mole is just a counting unit. That's what they're describing on what that is. Okay. So the mole is a counting unit, just like a dozen is. We don't usually order 12 or 24 ears of corn rather than the 1 or 2 dozen. Similarly, a chemist may want 1 mole of carbon or 2 moles of iron or 2.567 moles of calcium. In the sections that follow, and we'll be doing these calculations, okay, you will see how the mole relates to the mass of atoms and compounds. Okay. Then moving on to Avogadro's number. Okay, the number of particles in a mole has been experimentally determined in a number of ways. The best modern value is 6.022, like we said, times 10 to the 23rd, and we discussed that yesterday. And it's a constant known as Avogadro's number. Okay, they always refer to carbon 12, and that's why when you look at that table on the wall, that's why they're using carbon as the key, because that entire table is based off of carbon 12. Okay, because you may have heard of carbon 14. Why might that be utilized in the scientific community? Carbon 14 as opposed to carbon 12. Anyone? It's something that you probably heard of. It's just not very common to use. If you find something really, really old, why might you use a different form of carbon? Not carbon 12, but maybe carbon what? Carbon 14 dating. That's right. And what that does is carbon 14 is an isotope. What that means is you measure its half-life. Half the amount of carbon that will deplete itself in a certain amount of time. Then you put that in a mathematical formula that tells you, oh, this substance or this bone or artifact is 300,000 years old. I want to spew my age out there. So anyway. I realize we just had dinner, but we just come from study. We probably had a nap in the study hall. Wasn't quite long enough. Okay. Regardless. Okay. So Avogadro's number 6.022 times 10 to the 23rd. Okay. And molar mass, sometimes we'll refer to what we were maybe asking yesterday, but maybe not the correct terminology. Rather than utilizing some of these terms, maybe we should go over them, for instance. Like yesterday, one of the things we would say is we use sulfur as an example. So the molar mass of sulfur is 32.06 grams per mole. In other words, if you put 32.06 grams of sulfur in here, you have that counting unit of 1 mole that we just discussed. So molar mass is going to be that of the atomic masses either of one element or those added together. And a compound we did yesterday was magnesium nitrate. We take 1 magnesium, okay, 2 nitrogens, and then 6 oxygens. And again, one of the things that we have discussed is a lot of you are doing these higher order operations in mathematics and algebra 2. Unfortunately, some of these simple addition errors take place. I still make them as well. Okay? It doesn't reflect on intelligence. It's just, oh, shoot. Simple mistake. Those we can fix pretty easily. So please try not to get so discouraged should something like that happen. All right. So that's what a molar mass is. Any element on that periodic table, like silver is, I think, 107, copper 63. When we're talking about a molar mass, you're just given the atomic mass of that element or all of them added together in a compound. Okay, so we're going to start putting some of these to practical use. So what you see on the top of page 84, okay, there's a diagram there that's trying to illustrate or show you how to convert some of these masses of elements into grams, change them into moles, and also change them into atoms. Now, you could be looking at that and saying that makes absolutely no sense to me, and I can't disagree with that. I would say, yeah, that confuses me as well. But again, rather than memorizing something, I think it's more important to know how to use something like the periodic table. We don't have you memorize it. We just want you to know how to use it. Okay, so there's a gram to mole conversion. Some of these I just let you go through and read at a different time should you choose. We just want to go through some of the sample problems and then the practice ones. The sample one as well tells you how to do that. Very rarely go through them because it shows you the steps. See, I get the handy dandy teacher edition, so I get all the answers, but it doesn't show you how to do the work. You still have to do that. So, on the top of page 85, is anyone sitting out there thinking, oh my gosh, we are going way too fast? Okay, if that's the case, let me know and we'll go over something. This is being recorded at the same time. Should you feel that you need to maybe review something, that's entirely up to yourself. So, what we see on the top of page 85 says, what is the mass in grams of 2.25 moles of the element of iron? So what that means is we have to have a place to start. And you're only given one number, okay? And that is 2.25, okay? So what we are doing is changing this counting unit of moles into grams. And a lot of these numbers, we just don't pull out of the air. That's where you're going to be utilizing your periodic table. Like I mentioned earlier, I meant to print them out, but does anyone still have theirs from physical science? Okay. If you have that, you may want to retrieve it if you have it handy. It'll make things a little more, I want to say, easier on yourself. But if not, that's why there's a periodic table inside the back cover of your book that'll get us through today. And again, I try to need to remember to print off a new table. That'll hopefully be beneficial for yourself. Okay, but regardless, we've got this 2.25 moles of iron. Okay, so we got 2.25 moles of iron. So again, we really can't describe what a mole of iron is in this sense. It's just a counting unit. Okay? That's all it is. Don't get so hung up on the terminology. Oh my gosh, I don't know what this mole is. Again, just think of the example. It's just counting for 1 dozen, 2 dozen, okay, rather than saying 12, 24, 36, and so on. Okay, so this is what we start out with, okay, and it's asking what is the mass in grams, okay? So what we are doing is something called dimensional analysis, okay? The author writes these down, perhaps in the book, maybe just a little bit differently, where they may have it written like this instead, and they're going to put a multiplication sign there instead. But what this means is when numbers are next to each other, you multiply. And if they're on the bottom, you divide. Okay? So we're going to show you just this first time what it is that the author is illustrating and how we want to show this. Remember, we said there's 3 things that we can look at. The right way to do things, the wrong way, then there's our way. Okay? And what we're looking at this, it's not that this is the wrong way. To me, I think this makes things a little easier for yourself, but you're still more than welcome to do this bottom one as well. But it says, what's the mass in grams of 2.25 moles? So in this next step, if we want to cancel this mole out, do you think we would put that label on the top or the bottom to cancel it out? And we would put it on the bottom, okay? Because if we put moles up here, you're taking a mole times a mole, now you've got it squared. We don't want to do that, we want to cancel it out, okay? So we are going to put moles of iron on the bottom, okay? So mole of iron, and then we're referring to this as a molar mass, and sometimes the grams is on top, the moles is on the bottom. Sometimes the moles is on top and the grams are on the bottom. And we'll illustrate both of those. So remember the example we gave for this, if this beaker we were utilizing, we said if we wanted 1 mole of sulfur, how many grams would we put inside of here? When we look up at the periodic table, what would that tell you about sulfur? We put how many grams would give us 1 mole? 32. Okay, so every time you match up the mass with the atomic mass on the periodic table, that would give you 1 mole. But there again, this is just a counting unit. So for every 1 mole of iron, how many grams would you have? And again, we're just not pulling these numbers out of the air. You either need to turn to the inside back cover, periodic table from 2 years ago, or that one over on the wall. So what we're saying is, what is the atomic mass for iron? 55.85. Okay, so what we see happening then, just like what the author would show here, okay, these moles cancel here. Well, they do the same thing here as well. Once those moles have canceled, well then, what variable are we left with? What of iron? Grams. And remember what the question was asking is, what is the mass in grams of 2 1/4 moles? Okay, so these have canceled. We're just left with grams, and since these are next to each other, just like down here, what would you do with them 2 numbers? You multiply them and you're done. Yep. And the author says we should get around 126. Does that sound right? Yes? No? Yes, 126. Somewhere around there. Or 2.25 times 5.85 gives us 125.66. The author says 126, but we're going to do 125.67. 125.67. And the reason for that is we're rounding to the nearest 100. Okay? Every time. Round to the nearest 100. You may agree that as opposed to being as a freshman, we're going quite a bit faster. Okay, so left outside on the bus so far. Left middle, middle, right middle, right outside. Now this is one of those aspects to where if we're falling behind early, it's not going to get any easier down the road. So you've got this tool here. You can come in anytime before school. Might not be too conducive if we got cross-country practice, so we can certainly make arrangements. Come after school, whatever it is you think you might need to do to orient yourself in the direction that we need to be moving. Okay. So we'll go ahead. You can go ahead and pick, for instance, 2, 3, or 4. That's probably about all the time we have left. On page 85. Number 2 says, what is the mass in grams of 0.375 moles of the element potassium? So one of the things we get to do is it should be somewhere around 14.7. Okay, and that's moles of potassium. Well, one of the things that it may have these examples in the book, but if it doesn't show you how to do it, well then that can make things a little different or difficult. But one of the things you may catch on to, just like, why do we call that the periodic table? Do you remember from your freshman year, 2 years ago? What happens is it kind of like the days in a month, months in a year, okay? It's a pattern that keeps repeating itself. These types of problems, it's going to be a pattern of repeating itself as well, okay? So it's one of those aspects, if you're writing these down, and once we get to some of the problem-solving papers, okay, it's going to make it a lot easier for yourself to go back and do some of the examples. Oh, this is how we do this problem. We're going to add this compound together. We need the molar mass. We need to multiply, divide, what have you. Okay, so we got 0.375. And that's moles of potassium. Okay? Well, we're leaving this example up to refer to. We want moles to cancel in the second step, this counting unit. How do we get that to cancel? And again, that's with the molar mass. So what goes on the top here? You thought I was going to say the bottom. What might go on the top? You're exactly right, but why are you right? Again, we're not pulling these numbers out of the air. It's what? It is. It's the atomic mass of potassium. Right. So you correctly said 39.10. Is that right? Okay. 10 grams of potassium. That gives you an entire mole of potassium. Okay. So what do we see happening to these moles? They cancel. Okay. And what do we do with them two numbers? You multiply them out and we get what? 14.66. Yes, we'll take that. The author is rounding that up, but what a quinky dink, right? 14.66 grams then of potassium. All right. Temperature is a lot better in here than like yesterday. I mean, that's probably a silly rhetorical question, but anyway. So if you're feeling confused about these, I strongly urge that we rectify that situation sooner rather than later. Good? All right. We will probably pick up with, there's 3 different types of problems that we deal with. Moles to grams, grams back to moles, and possibly grams all the way to atoms. That's a 3-step problem. We're just showing you 2 steps right now. This is step 1 and then 2. We'll get to that probably tomorrow. All right. You can do